I think you know that our planet moves not only around the sun, but also moves around the center of our galaxy. But the galaxy doesn't stand still either, so where does it go? You're about to find out where we're going and at what speed we're moving. But more briefly, we are on planet Earth, which revolves on its axis and around the sun. The sun rotates on an elliptical trajectory around the center of the Milky Way, which within our local group stretches towards Andromeda. The local group, in turn, moves within our cosmic Laniakea superscope, by galactic groups, clusters, and cosmic voids, and they lie in the KBC Howdah, in the middle of the structure of the universe on a large scale. First, let's look around and get to know our neighbors in the universe. We have learned a lot in the last few decades, and the word cosmography today is not a term from Strugatsky's science fiction novels, but one of the sections of modern astrophysics that deals with mapping the part of the universe available to us. The nearest neighbor of our Milky Way is the Andromeda Galaxy, which can be seen in the night sky and the naked eye. But to see a few dozen more companions will not get dwarf galaxies that orbit around us, and Andromeda very faint. And astrophysicists are still not sure that they have found them all. Nevertheless, all of these galaxies, including the undiscovered ones, as well as the Triangle Galaxy and the NGC 300 galaxy, are part of the local group of galaxies. There are now 54 known galaxies in the local group, most of which are the already mentioned dim dwarf galaxies, and its size exceeds 10 million light-years. The local group, along with about 100 other galaxy clusters, is part of the Virgo supergroup, which is more than 110 million light-years in size. In 2014, a group of astrophysicists led by Brent Tully of the University of Hawaii found that this supercluster itself, consisting of 30,000 galaxies, is a component of an even larger structure, the Laniakea supercluster, which already contains more than 100,000 galaxies. It remains to make the last step. Laniakea, together with the Perseus-Pisces superscope, is a part of the complex of superscopes Pisces-Keith, which is simultaneously a galactic filament, that is, a component part of the large-scale structure of the universe. Observations and computer simulations confirm that galaxies and clusters are not chaotically scattered in the universe, but constitute a complex sponge-like structure with filamentary filaments, knots, and voids, also known as voids. The universe, as Edwin Hubble showed almost a century ago, is expanding, and superclusters are the largest formations that are held together by gravity from scattering. That is, to simplify, the filaments are scattering away from each other due to the effects of dark energy, and the motion of objects within them is mostly due to the forces of gravitational attraction. And now, knowing that there are so many galaxies and clusters around us, which attract each other so strongly that even outweigh the expansion of the universe, it is time to ask the key question: where does it all go? That's the question a group of scientists, along with Yehudi Hoffman of the Hebrew University of Jerusalem and the already mentioned Brent Tully, are trying to answer. Their joint paper, which appeared in Nature, is based on data from the Cosmic Flows 2 project, which measured the distances and velocities of more than 8,000 nearby galaxies. This project was launched in 2013 by the same Brent Tully along with colleagues, including Igor Karachentsev, one of Russia's most highly cited observational astrophysicists. So where is it all going? The answer requires an accurate velocity map for all massive bodies in the near universe. Unfortunately, the Cosmic Flows 2 data are not sufficient for its construction. Despite the fact that it is the best that mankind has, they are incomplete, heterogeneous in quality, and have large errors. Professor Hoffman applied Wiener estimation to the known data, a statistical technique for separating the useful signal from the noise, which comes from radio electronics. This estimation allows us to introduce the basic model of the system behavior. In our case, it is the standard cosmological model, which will determine the general behavior of all elements in the absence of additional signals. That is, the motion of a particular galaxy will be determined by the general provisions of the standard model if there is insufficient data for it, and by measurement data if there are any. The results confirmed what we already knew. The entire local group of galaxies is flying through space toward the Great Attractor, a gravitational anomaly at the center of Laniakea. And the Great Attractor itself, despite the name, is not so great. It is attracted by the much more massive Shapley supercluster, towards which we are heading at 660 kilometers per second. The problems began when astrophysicists decided to compare the measured velocity of the local group with the calculated velocity, which is derived from the mass of the Shapley supergroup. It turned out that, despite its colossal mass, 10,000 masses of our galaxy, it could not accelerate us to such a speed. Moreover, by constructing a map of anti-velocity, a map of vectors that are directed in the direction opposite to the velocity vectors, scientists have found an area that seems to repel us from itself. Moreover, it is located exactly on the opposite side of the Shapley supercollapse and repels exactly at the speed to give a total of the desired 660 kilometers per second. The whole attractive repulsive structure resembles the shape of an electric dipole, in which the lines of force go from one charge to another. But it contradicts all the physics we know. Anti-gravity can't exist. What kind of a miracle is this? For the answer, let's imagine that you are surrounded and pulled in different directions by 5 friends. If they do it with the same force, you will stay in place, as if no one is pulling you. However, if one of them, standing on the right, lets go of you, you will shift to the left, in the opposite direction from him. In the same way, you will shift to the left if the 6th friend joins the 5 pulling friends and stands to the right and starts pushing you instead of pulling you. This may be a rather strange example, but it is true. The FTL engine works on a similar principle, but we'll talk about it later. In fact, you could say it's simpler than that. In one place, we have a huge accumulation of dust, gas, stars, galaxies, etc. And in another place, we have something that acts the opposite way, like anti-gravity, which repels us. There's a lot of this antimatter in that place too. Thank you for watching to the end. Don't forget to like and subscribe to the channel to learn more about space.